Hey everyone, we are continuing to introduce the idea of circuits and the key concepts behind them. In this video, we are going to learn about the idea of electrical current as well as electric resistance. So let's jump in. Before I get into electric current, I just want to remind ourselves of where we are from the last video. Hopefully you should recognize what an electric circuit is. It's a path for electrons to travel, kind of by design, so that they can power certain things. Here I have a circuit that we saw in the last video. It has a 9-volt battery here, and it's powering a light bulb. Now, there's electrons all throughout the circuit itself. There are electrons in the wire, in the light bulb. If there's an electron right here, in fact, there's millions and billions of them. When I plug in that battery, this electron is going to start moving this way, to the right, because the battery has a positive side and a negative side. There's a chemical reaction going on that's essentially always making this a positive terminal, a positive side. This a negative side. We know electrons are repelled from negatives, so it would move this way. It's going to move kind of counterclockwise. We also hopefully know that those charges are given energy from the battery. It's known as voltage or potential difference. All right, 1 volt is how much energy each unit of charge is given. And they have to use up that energy when they complete their path. So if this battery is giving electrons an additional 9 volts, or if it's giving every coulomb of charge, 9 joules of energy, that must be used up. It's probably being used up by this light bulb right here. Okay? So electrons are moving, they're repelled by the negatives, attracted to the positives. They're also given energy in the form of voltage from these batteries. Now, when electrons are moving, we can talk about how many electrons are moving. That's where the first part of this video comes in, electric current. Electric current describes the flow of electrons. And this is really pretty straightforward, especially if you think of a great analogy, water. Here I have like a raging river. There's a lot of atoms and molecules of water flowing by. Here I have just the slightest trickle of water. So here I have a very large amount of electrical current. Of water current. Here I have a very small amount of water current. It's the same thing for circuits. When you have more electrons passing through a given point, you have large electrical current. If you have a small amount of electrons passing through, you have a small amount of current. Okay, I'm going to go to my next video, but I'm actually going to pull up our good old Phet simulator. Here I have a basic circuit. I have a battery right here. This is the positive end of the battery. This is the negative end. Here we see those electrons. Remember, they already exist all over. They're moving through. They're moving with kind of a certain speed, so to speak. It's not exactly speed that's electric current, but we can see the rate kind of these electrons as they're moving through the wire. If I had a person right here, they were literally counting how many charges pass through in a given amount of time, that would tell them the current that was involved. I can actually change the current. We're going to increase the voltage of this battery. Look, oh my gosh, now more charges would be passing this spot right here in a given unit of time. So the electric current, the flow of electrons, would be increasing. Let me bring that back down to 9 volts. We'll use that a little later. Okay, now, current, there is an equation for. We'll actually see current a couple times. There's a symbol. It's just uppercase I. The symbol for current is I. I believe they use the letter I for the French intensity, or the French version of intensity. And I, current, is just the amount of charge, which, remember, we measure in coulombs, in a certain amount of time. This is the equation you'll see on the AP equation sheet. So this here is just time. So the units are coulombs over seconds. You could write down, a circuit has a current of 5 coulombs per second. That's a bit of a mouthful. So they've named coulombs per second after a physicist named Ampere. All right, so the unit for current is amperes, 5 coulombs per second or 5 amperes. To be honest, even the phrase ampere, the term ampere is kind of long. That's usually abbreviated to amps, which I'm guessing a lot of you are familiar with. Electric current is measured in amps. Okay? Now, we know that electrons flow toward the positive end of the battery. Again, here's my diagram right here. If I looked at my little electron, it would be repelled from this negative side, because like charges repel, and it would be attracted to the positive side. Electrons would be flowing this way, counterclockwise. An electron right here would be going this way. Electron right here would be going this way. All right. However, Benjamin Franklin. Yes, that Benjamin Franklin. He studied electricity. And when he was studying current, he assumed it was the positive charges. This is the year 1752. All right, we weren't zoomed in on wires and we couldn't see that it was electrons moving around. We know things today that Ben Franklin did not. He thought it was the positive charges that were flowing. And therefore, if it was the positive charges, well, if I looked at a positive charge right here, it wouldn't move to the left, it would move to the right. By convention, due to Benjamin Franklin, it's his fault. Conventional current, letter I, that's conventional current, is actually the direction protons would move, which is very weird and is in fact incorrect. So by definition, conventional current would be flowing this way. Electron current is flowing the opposite way. In real life, what's physically happening is what I have drawn in red. Electrons would be flowing toward the positive side. However, if you become an electrical engineer, or if you become an electrician, or if you study more physics in college, you're going to see a lot of diagrams where they have current seemingly pointing in the wrong direction, toward the negative terminal. That's because by convention, we use the direction of Ben Franklin's current, conventional current. If, and luckily on the AP test, I've never seen them ask this question, but if you ever saw a question that simply said, what is the direction of the current? Maybe they gave you this picture. If they ask it this simply, you should always choose the direction for conventional current. Current is defined as the direction positive charges would be moving, even though they aren't moving. You would pick the quote-unquote correct answer if they say, what is the direction the electrons move? Okay, again, you're probably not going to see this question, and it's not actually going to change any of our math or understanding of future topics. Okay, but just know you might see diagrams that seem to go against what you've been told about electrons moving towards pluses and away from minuses. It's just because they're using conventional current as the direction of I. Okay, second topic. Resistance. Resistance is pretty straightforward. It's something that impedes the flow of electrons. And again, I'm going to go back to my water analogy. We could have water flowing down a river, but if we have something like a beaver making a dam, that dam is impeding. It's preventing water from flowing. The dam causes resistance in that water. For electricity, you can have resistance in wires. You can have resistance in light bulbs and the filaments of bulbs, inside the circuitry when you have your smartphone or a computer. Resistance is either not by design, you don't want it, or sometimes we kind of want to throttle back how much electricity is flowing. We might want to actually add resistance in a circuit. Resistance could be due just simply to the atomic structure of material. I have right here a representation of copper. And copper has a lot of electrons. Remember, electrons don't like each other. So these electrons that are really far away, they don't really like being here next to these other electrons. They're far away from the positively charged thing that they do like. It's easy for these electrons to drift around. They have a very low resistance. Whereas over here, I have styrofoam. Styrofoam, I'm going to spell that wrong. Or at least this is the chemical composition of styrofoam. Styrofoam is made up of strings of carbon and hydrogen. Now, hydrogen only has one electron normally, okay? And that electron is very close to its proton that's in the nucleus of hydrogen. Carbon has 6 electrons, but they're all still pretty close. And for styrofoam, all of these electrons are locked in bonds. It is very, very difficult for the electrons in styrofoam to move around, to flow. That's why we don't make wires out of styrofoam. Styrofoam is an insulator. Okay, so the atomic structure alone, even though you're never going to be asked, why is styrofoam an insulator? That won't show up on the AP test. Also, things like temperature can affect resistance. Raising the temperature can raise the resistance. Impurities in the material, corrosion, rust, things like that. Okay, we're not really going to get into the physics of these things too much in this course, and you're never going to be asked specifically about this. Just know that resistance can be dependent upon the material. There is going to be an equation, so there's a mathematical symbol. It's uppercase letter R. Resistance was measured famously by a physicist with the last name of Ohm. What a fantastic last name to have if you're a mathematician or a scientist. So they've named the unit of measurement of resistance after him. So we measure resistance in something called ohms. That's abbreviated not with uppercase O, but with upper Greek letter case, ohm. This is how you draw uppercase letter ohm. Looks kind of like an upside down horseshoe. Okay. Now we're on our second to last slide. For a material, we're mostly going to use this by looking at wires, but this is actually true in most material. For a wire, we usually assume that they're ideal, that there's no resistance. But in real life, wires and all material have some amount of resistance. And that resistance is based on three things. And this equation is also on the AP Physics 1 equation sheet. Here I have R for resistance. Remember, this is going to be measured in something called ohms. Resistance for a material is based on three things. First, this is lowercase Greek letter rho. We've actually seen it before. This is resistivity. This is just going to be some constant for a material. Okay, for example, copper has a resistivity of something like 10 to the negative 8. All right. Wood, or air, I should say, air has a resistance of times 10 to the 15. So obviously, if you have more insulators, they have a higher resistivity than conductors. A superconductor, if you've ever heard of that term, superconductors have resistivities of 0. That's kind of the definition of a superconductor. You need very low temperatures to get resistances and resistivities of 0. It also depends on the length of material, and kind of think of like a traffic jam. If you have a longer road or if you have a longer traffic jam, it's going to take you more time to get through all of that. So if you have more material you have to get to, that usually means, or it does mean, that the resistance is going to be greater. And the last thing is A, that's cross-sectional area. That's like this area right here that I'm filling in. All right, you could probably guess that if you have a wider pipe, if you have a thicker material, well, that's more room for things like electrons to pass through. You could have more water flowing through this thick pipe than through this narrow pipe. Okay, think of also the road. If you have just a one-lane road, you can only squeeze one car in a lane at a time. If you have a much wider road, 3 lanes, 4 lanes, 5-lane highway, more cars can pass, so you have less resistance. To be honest, very rarely on the AP test are you going to just plug in numbers to solve using this equation. Often they'll ask like, oh, which of these two pipes will have more resistance? Or we'll do one of those questions where, like, if you double the length of the wire or the material, will the resistance increase or decrease? Those types of questions. But this equation is on the AP equation sheet. And you would not be expected to memorize the resistivity of any material. They'd either give it to you or you'd be asked to solve for it. I only have one more slide for you, and it's just to go over a common misconception that I want you to not have when it comes to current and resistance. Again, I have my circuit drawn right here, and this was the positive side, this was the negative side. The current in a single path, and all the circuits we've looked at have just had this simple singular path. The electrons are moving like this, counterclockwise. Remember, conventional current is moving in the opposite way. This is the direction the electrons are moving. We do have something that has resistance, this light bulb. Light bulbs function with resistance, most light bulbs with filaments in them. Okay? I don't want you to think that the electrons, they fly through these wires and then they slam to a halt when they meet a resistor, something that's causing resistance, and then they continue flying forward. In a single path like this one, the resistance is constant. I'm going to go back actually to my demo right here. And in this demo, we see that the electrons are moving and they have a very certain flow rate. They have a certain current. It's not like flying through the wires here and then bunching up. This is not happening. Thank you, Giphy, this website. I love this little animation. Okay, this is not what's happening. Electrons are not flying through the wire and then bam, they hit some resistance. And then after that resistance passes or they pass it, they continue flying. This is not what's happening. It's all because, remember, electrons are everywhere already. The wires are not hollow tubes. There is this steady march going on. I like this picture. Think of it as a circular march of penguins. There's some resistance that's going to slow down these penguins, but it's going to slow them all down together. If I go back to my window right here, here I have this wire, this circuit with a 9-volt battery. Here I have another circuit also with 9 volts. Notice that the current is smaller in this circuit. These electrons are moving slower than in this circuit, where they're moving a bit faster. That's because in this circuit there's only one resistance, one piece of resistance, one light bulb. Here there's 3. So the current is definitely slower in this circuit, but it is not like these electrons are flying through, slamming to a halt, slowly crawling, then speeding up again. Again, I have my march of the penguins. If these electrons get slowed down because of these resistors, these things causing resistance, that's going to slow down these electrons and these electrons and these electrons and these electrons, all the electrons in this single path. Okay? The current in a single path stays constant for a given circuit, even if all the resistors are just on one side, because they're all jammed together. We have this penguin march. A slowdown in one spot instantly causes a slowdown everywhere else. All right? So that's current and resistance. Thanks for watching.